yesterday I started to discuss the stability condition of the time path of income in context of Samuelson framework. Also, I mentioned something about what will be the nature of the time path. So basically, two equations are important. Alpha beta is equal to 1. This equation is important. If alpha into beta is less than 1, in that case, we are finding the time path will be stable. And if alpha into beta is greater than 1, in that case, the time path will be unstable. That was the feature. And then we considered one more condition in terms of the discriminant of the equation. So I mentioned that if roots are real, that is beta greater than equal to real and distinct, real and repeated, that is beta greater than equal to 4 alpha by 1 plus alpha whole square. In that case, the time path will be monotonic. Otherwise, the time path will be complex conjugates. Now, before presenting all these things graphically, I feel that once again, I'll clarify the stationarity condition or stability condition or the convergence condition, as well as the condition which will indicate whether the time path will be monotonic as well as oscillatory. Okay, monotonic as well as oscillatory. Okay, because last day, while I discussed the stability condition, I mentioned only about the distinct real root case. However, I didn't mention anything about the context when the roots are complex conjugates. When I discussed the nature of the time path, I discussed about, what will happen if the roots are complex conjugates. However, the stability condition, when I presented the stability condition, I presented the thing only in terms of real roots, not in terms of complex roots, isn't it? So I need to complete that part. I need to add some more points at that juncture. So I hope these things are clear to all of you. B1 plus beta, B1 into beta, then 1 minus B1 into 1 minus B2. So these concepts are clear, I hope, to all of you. And from the last thing, 1 minus B1 into 1 minus B2, which is equal to 1 minus beta, as beta, which is the MPC, lies in between 0 and 1. Safely, we can present 11a in this format. 1 minus B1 into 1 minus B2 lies in between 0 and 1. And then I started to talk about the convergence issue. And I mentioned about the roots when they are real and distinct, Okay. So when the roots are real and distinct, I mentioned their product. I mentioned about their product B1 into B2, okay, which is equal to alpha beta. That would be greater than 0. B1 into B2, which is equal to alpha into beta, that will be positive. If the roots are real and distinct, in that case, product of two roots will be positive. That indicates B1 and B2 will possess either positive sign or negative sign. Both will have the same sign. Okay. And then I talked about B1 plus B2, which is beta into 1 plus alpha, which is greater than 0. Beta into 1 plus beta is positive, alpha accelerator positive. So beta into 1 plus alpha, that is greater than 0. Okay. Now, if B1 plus B2 is greater than 0 and the product is also greater than 0, which indicated the roots will have the same sign, Now, if I say B1 plus B2 will be also greater than 0, in that case, B1 and B2 can only be positive. B1 and B2 can only be positive. Okay. And following the complementary function and following the structure of the time path, we indicated the stability condition, which is given by mod B1 less than 1 and mod B2 less than 1. Both mod B1 and mod B2 less than 1. Okay, so combining all these things, in case of real roots, since B1 and B2 both are positive, this implies their product B1 into B2, which is equal to alpha beta, should be less than 1 when mod B1 less than 1, mod B2 less than 1. If mod B1 less than 1 and mod B2 less than 1, that is absolute value of both the roots are less than 1. In that case, their product, which we defined as alpha into beta, that should be also less than 1, or beta should be less than 1. Multiplier will be less than 1 upon the accelerator. And we marked this as the required condition for stationarity, required condition for stability. Okay. However, I didn't say anything when the roots will be complex conjugates. I started with, B1 and B2 are real and distinct, real and distinct. However, I didn't mention anything about the context when the roots will be complex conjugates. So please look at the rule. When B1 and B2 are complex conjugates, we consider the absolute value R, which is equal to root over alpha beta, where alpha beta is the absolute coefficient of yt minus 2. That is the highest order of the difference equation. So what is the rule in case of second order difference equation or higher order difference equation? I have to check the coefficient associated with yt minus 2. I have to consider the coefficient associated with yt minus 2. Okay, absolute value of the coefficient associated with the highest order of the concerned variable. Here, highest order of the concerned variable is yt minus 2. Okay, second order lag. Okay, so I have to consider the absolute value related to yt minus 2, which is alpha into beta, alpha into beta. Okay, and we need to consider the square root of that. If you look at this equation, this equation, then also if you consider in terms of the characteristic equation, then also the coefficient associated with b to the power t minus 2 is nothing but alpha beta. The absolute value of the coefficient is alpha beta. Better to consider the original equation, which is equation number 5, and check what is the coefficient associated with yt minus 2. Okay. So again, I am repeating, when B1 and B2 are complex conjugates, we consider the absolute value R, which is root over alpha beta, where alpha beta is the absolute coefficient of yt minus 2. R can be theoretically greater than, equal to, or less than 1. Among all these possibilities, the time path will be stable if and only if R is less than 1. This in turn implies the product alpha into beta that is less than 1, which in turn indicates beta is less than 1 upon alpha. So if the roots are real, then also the equilibrium condition is beta less than 1 upon alpha. If the roots are complex conjugates, then also the stability requirement is beta less than 1 upon alpha. Yesterday, I didn't mention about this part. I didn't mention about this part, okay? So be careful about all the possibilities, because roots may be real, roots may be complex conjugates, and when we are defining stationarity, we should define stationarity in terms of both the possibilities, when the roots are real and when the roots are complex conjugates. Any question? Is it okay?
Ma'am, can you just wait 30 seconds?
Would you be a bit louder?
Ma'am, can you just wait 30? What you said.
Will anyone just tell me what she is trying to tell?
Ma'am, she just said if you'd wait for 30 or 40 seconds.
Okay.
Yes, ma'am, I'll just read it once.
Is there anyone who could not understand the matter? Those who were not there in the class yesterday, for them, actually, you need to go through the entire thing. Then only you will understand the matter. It's very difficult to understand one condition out of the entire model. And then I started to talk about the nature of the time path, which will depend on discriminant of the roots, the discriminant, which is below the root over part. It will depend on that fact. So if the roots are real, that is beta square into 1 plus alpha whole square, minus 4 alpha beta greater than equal to 0, or in other words, beta greater than equal to 4 alpha by 1 plus alpha whole square. Now, when I am considering greater than equal to, I am considering real distinct and real repeated, both the possibilities. Real distinct and real repeated. If we look at the root values, when the equality sign will possess between these two parts, in that case, the root values will be beta into 1 plus alpha by 2. Only this part, beta into 1 plus alpha by 2. So in that case, the roots are real. However, the roots are repeated. Stationarity condition will not change. That will depend on the, structure alpha beta less than 1. If the roots are real, be it distinct, be it repeated, the stationarity condition is alpha beta less than 1. Okay. So separately, I do not need to mention anything about this thing. However, when I am handling the discriminant and trying to find out the nature of the time path, remember that when I am talking about real, I'm taking care of real distinct and real repeated roots, real distinct and real repeated roots. So whenever beta is greater than equal to 4 alpha by 1 plus alpha whole square, that is, roots are real. They may be distinct, they may be repeated. In that case, the time path will be monotonic. As long as beta greater than equal to 4 alpha by 1 plus alpha whole square, the time path will be monotonic. However, if beta is less than 4 alpha by 1 plus alpha whole square, in that case, the roots will be complex conjugates and the time path will be oscillatory. So remember that when the roots are real, the time path will be monotonic. When the roots are complex conjugates, the time path will be oscillatory. Okay. Now, on the basis of the stationarity condition, that is alpha beta less than 1, and on the basis of whether beta greater than equal to 4 alpha by 1 plus alpha whole square or beta less than 4 alpha by 1 plus alpha whole square, we will try to divide alpha beta plane into several zones, and we will try to check in which zone the time path will be monotonic convergent, monotonic divergent, damped oscillatory time path, explosive oscillatory time path, uniform oscillatory time path, of income, etc. So in the next step, I have to draw two curves, alpha beta equal to 1 and beta equal to 4 alpha by 1 plus alpha whole square. So I'll draw two curves, alpha beta is equal to 1 and beta is equal to 4 alpha by 1 plus alpha whole square. Now alpha beta is equal to 1. That will be a rectangular hyperbola. If I have the alpha beta plane, just if I have the alpha beta plane and if I have the equation alpha beta is equal to 1, what will be the shape of this equation?
A rectangular hyperbola. Rectangular hyperbola.
Okay, so this kind of curve I'll draw. I'll show you the diagram, just I'm discussing the matter. In the alpha beta plane, alpha beta is equal to 1 will be greater than, alpha beta is equal to 1 will be given by a rectangular hyperbola. So in this zone, alpha beta will be greater than 1 or beta greater than 1 by alpha, and in this zone alpha beta less than 1. So if I have any time path in this zone, okay, that will be convergent in nature. It can be monotonic, it can be oscillatory. However, if alpha beta is less than 1, it is satisfying the stability condition or stationarity condition, and for that matter, the time path will be convergent. On the other hand, if I get something above this line, above this boundary, in that case, the time path will be divergent in nature. The time path will be divergent in nature. In fact, if I get alpha beta equal to 1, in that case also, we will not get convergence. We will not get convergence. Stationarity or convergence is possible only for strict inequality, alpha beta less than 1. If alpha beta is strictly less than 1, we will have the convergent time path. Otherwise, we will have a divergent time path, okay, non-stationary time path. It will not converge towards the equilibrium value. The other equation, as I am telling you, beta is equal to 4 alpha by 1 plus alpha whole square. Okay, you can consider would you please derive the value and tell me what is the value? First, dB by d alpha, d beta by d alpha. You can use U into V format, 4 alpha into 1 plus alpha to the power minus 2.
And denominator is 1 plus alpha to the power 4.
What is the denominator?
1 plus alpha to the power 4.
1 plus alpha to the power 4.
Yes, ma'am, by U by V.
Square the denominator.
Ma'am,
So,
with 1 alpha plus 1 not be cancelled out.
First, tell me the entire thing you got. After that, I'll.
okay, numerator is 8 into alpha তারপর bracket 1 plus alpha minus 1 plus alpha whole square into 4 minus 4 1 plus alpha whole square.
Minus 4 into
1 plus alpha whole square.
this thing.
Yes, ma'am.
So everybody got this?
Yes.
Therefore, I thought, you can take 1 plus alpha common. So if this is the value everybody got, eight alpha minus 4
Ma'am, actually it will be 4 1 plus alpha square minus 8 alpha.
Yes, ma'am.
Getting 4 1 minus alpha over 1 plus
Minus
alpha
sign
cube.
can.
Yes, ma'am.
So if I do the thing, I'm getting 4 alpha
4
or
1
minus 1.
Ma'am, I'm getting 4 1 minus alpha by 1 plus
Over
alpha.
1 plus alpha whole cube. Shouldn't it be 1 minus alpha?
Yes, ma'am. 1 minus alpha.
Yes, ma'am.
So everybody is getting this?
Yes, ma'am.
Yes, ma'am.
4 into 1 minus alpha divided by 1 plus alpha whole.
No. 4 into alpha minus 1. Ma'am.
You are getting alpha minus 1 from this 2.
8
Minus-
alpha minus 4 minus 4 alpha. So 4 alpha minus 4, that is equal to 4 into alpha minus 1.
Yeah, from your calculation, I am getting that. However, rest of the students are telling it is 1 minus alpha. 1 minus alpha is coming.
Ma'am, actually what happened is we du minus du that way. So please remove calculation, just the minus sign
When
is
you
that.
do that thing, tell me the final result, okay? Anyway, you can do the thing. Because from this equation, what I am finding, 8 alpha minus 4 alpha, that means 4 alpha minus 4. Okay. So it is 1 minus alpha. And, sorry,
Alpha minus 1.
yeah. And some students told me they are getting this. Since I didn't do this thing in my own, therefore I am asking whether it is alpha minus 1. From this equation, I am getting this value. 4 into alpha minus 1 divided by 1 plus alpha whole cube.
Ma'am, it is 1 minus alpha.
Yes, ma'am. It's 1 minus alpha.
Yes,
Ma'am, it's 1 minus alpha.
Ma'am, it is up to
Problem in this calculation then.
Yes, ma'am. It's
Yes.
actually Shubhayan did it correctly, but he just switched the terms but didn't switch the signs. So that's
Vanita,
why,
please tell me where I need to make a change.
ma'am. So basically, I mean, I'll tell you the entire calculation. So basically, if we use the rule, we'll have in the denominator 1 plus alpha to the power 4. And then in the numerator, we'll have 1 plus alpha square times 4 minus 8 alpha times 1 plus alpha. And then if we solve this and simplify, if we take 1 plus alpha 4 common, basically, in the numerator, then we get 4, 1 minus alpha.
Coefficients, as
Sorry, ma'am.
there is some problem. Would you please present the thing?
Ma'am, I can't. I'm on a laptop.
Okay.
If Upanita, can you present if you are okay? Okay.
So rest of the students will be able to check it. Anyone? You can present it. Not visible at all. একটু focus করতে হবে. Students, are you getting this? I'm not getting it properly.
Ma'am, if it's fine, can we use the whiteboard application and just show it on the screen?
Yeah, why not?
Ma'am, can I just show the solution on the screen?
Anyone whose opinion is rightly done, maybe. However, it is not visible.
Upanita, let it be. I think Udita is showing.
Please show it to us. Okay, so d beta by d alpha. Everybody please check whether you got the same thing or not. It is visible, so please check this thing. The last line is not right. There is a mistake in the calculation. It is not 4 by 1 plus alpha. So there is a mistake in the calculation. So this is not the right calculation. Udita?
The last line is wrong because I was trying something else and forgot to cut it out.
Okay, so
Okay, ma'am. Then I'll stop presenting.
Sharing something, So Udita, would you please stop presenting because there is a mistake. So Priyasha, how people will check the Jamboard?
Ma'am, I'm just turning it on. 1 second.
Show this thing to us.
It's not opening. It's saying the pop-up is being blocked.
I have to click.
Ma'am, can I present? I logged in from my phone.
Okay, so I'm not getting anything.
Shall I show?
Yeah. Who are you?
Prithviraj.
Yeah, Prithviraj. Yes, definitely. And those who could complete the first order rightly, you can check the second order too. একটু বড় করা যাবে কি? Okay. So is it visible to everyone?
Yes, ma'am.
Alpha? 1 plus alpha whole square into 4 minus. Okay. So there was a mistake, you know, the second term came first and the first term came second. That was the problem in the earlier calculation. Okay. So I think this is the right one. 4 into 1 minus alpha divided by 1 plus alpha whole cube. This is the right one. So everybody, please check this thing. This calculation is perfect and visible too. Many of you did the right calculation, however. So it is 4 into 1 minus alpha divided by 1 plus alpha whole cube. Thank you, Prithviraj. So the value can be positive, the value can be negative, you know, because if look at the numerator, if alpha is greater than 1, in that case the value will be negative, and as long as alpha is less than 1, the value will be positive, isn't it? Everybody?
Ma'am, can you please just repeat what you just said?
Yeah. Just let me. Okay, so finally we are getting the value to be, you know, d beta by d alpha. This is equal to 4 into 1 minus alpha divided by 1 plus alpha cube. Okay, so if what will be the sign? What will be the sign?
Negative.
If alpha is less than 1?
Positive.
No, ma'am, positive.
Positive.
Yes. On the other hand,
Negative.
okay. Okay. And would anyone please calculate? Or everybody, you know, it is better.
Ma'am, it's coming as 4 into alpha minus 3 by 1 plus alpha cube.
4 into alpha
Alpha
minus
minus 3 by 1 by alpha 1 plus alpha cube.
this one.
Yes, ma'am.
So let other people do this thing quickly. If you just find out the slope, then also it will work, you know. I don't need, in fact, the second order condition as such. I need the first order condition. That is, it is positively sloped up to a certain point and negatively sloped after that. So I need that kind of thing. Okay. So you may do this thing, you may not, you know, the second order condition is not that required, you know, here. So I actually don't need it. Okay, so you may not calculate this. What I need, I'm showing the things in graph. This is this line. And can you tell me when the two lines alpha beta equal to 1 and this line, you know, beta is equal to 4 alpha by 1 plus alpha whole square.
1, 1.
Intersect each other? Can you tell me when the two lines will intersect each other?
Ma'am, 1,
Ma'am,
1.
when alpha is equal to 1.
Yes, and beta
Yes.
is equal to? When alpha is equal to 1, then beta is equal to?
1.
1.
Okay. So at 1 coordinate, the curves will intersect each other. So I'm marking the point. For the second curve, that is beta is equal to 4 alpha by 1 plus alpha whole square. For alpha less than 1, the curve is positively sloped. Then the lines are cutting each other at this point, and the line will be negatively sloped if alpha is greater than 1. So are we getting this kind of curve then? Everybody? One curve is like this, and the other curve is like this, isn't it?
Ma'am, the other curve is for what I couldn't catch.
The other curve?
Is for what I couldn't catch it.
For alpha less than 1, d beta by d alpha is greater than 0. Okay, so for the line beta is equal to 4 alpha by 1 plus alpha whole square. This is first one. This line, sorry, this line. So beta is equal to 4 alpha by 1 plus alpha whole square. As long as alpha is less than 1, the curve is sloped. And when alpha is greater than 1, the curve is negatively sloped. So I am getting a line which is first positively sloped and then negatively sloped.
Okay, ma'am.
Okay. So for beta is equal to 4 alpha by 1 plus alpha whole square, I am getting this kind of curve. Everybody?
Ma'am, but without this second derivative, how will get the exact curvature?
I am not talking about the curvature. If I can talk about the slope, then also it is fine. I do not need to check, in this case, whether it is concave, etc. Because if I get the first order condition, on the basis of that, I can say it is first positively sloped and then negatively sloped. Now you can also consider the second order condition to check concavity of the curve. As such, I do not need the second order condition here. However, there is no issue if you check the second order condition too. And if you look at the second order condition, in that case, the denominator is positive. However, specifically, it is a bit difficult to say what will be about the numerator because, it is alpha minus 3. If it is positive.
Ma'am, it's not alpha minus 3, it's alpha minus 1.
It's alpha minus 1, the second order condition.
Yes, ma'am.
This is the second order derivative.
No, ma'am.
So I need to calculate this, because people are telling different formula. So here actually, I may check the concavity thing, I may not. If I look at the slope, then only we are getting this kind of curve. I am getting a curve which is first positively sloped and then negatively sloped. Okay, so parabolic kind of thing, parabolic curve. Whenever we have a quadratic, generally it will be a parabola. So it's not necessary to check the second order condition. However, you may check it and you will find that, or we should have the second order condition, which is indicating a bowed down kind of curve. So number one, since it is a quadratic, it will be parabolic in nature. Number two, the lines are cutting each other at the points alpha beta is equal to 1. And when I'm checking the slope of the curve, as long as the alpha value is less than 1, the curve is positively sloped. Otherwise, the curve will be negatively sloped, you know. So we will have a parabolic curve, bowed down curve, a bowed down curve towards the horizontal axis. So it will give us a parabolic shape. Okay, so keeping all these points in our mind, I can plot the two curves. So this is the diagram. This is the diagram. Alpha beta is equal to 1. I am calling the line PQ. Actually, the points above 1, 1 is not relevant. We need the interaction of both the lines. So, you know, this zone is the relevant zone. Therefore, the other part of the rectangular hyperbola, I kept dotted. The solid part is relevant for our analysis, and I'm marking this as PQ. This PQ part is relevant. Regarding the other curve, the second line will intersect the first line at the point 1, 1. Alpha is equal to 1, beta is equal to 1, number 1. And it is first positively sloped and then negatively sloped. And in general, you have the idea, when we consider a quadratic, it should look like a parabola. So together the two curves can be presented in this way. And I am marking the red one as OPR. The red one, that is beta is equal to 4 alpha by 1 plus alpha whole square. This curve I am marking as OPR. So everybody could draw the diagrams. Is it okay?
Yes, ma'am.
Okay. So once you draw this diagram, you know, as I mentioned, for the rectangular hyperbola in this zone, I have, and in this zone, I have alpha beta greater than 1. So below the things, you know, I'm dividing the zone on the basis of the red and the black lines. I'm dividing the zone into two parts, 1 and 2. In zone 1, as you are finding, alpha beta is less than 1 and beta greater than 4 alpha by 1 plus alpha whole square. Okay. So this entire zone, when alpha beta less than 1, that I am dividing into two parts, 1 and 2. In zone 1, alpha beta less than 1 and simultaneously beta less than 4 alpha by 1 plus alpha whole square. Whereas in these zones, zone 2, you know, in zone 2, alpha beta less than 1. However, beta is less than 4 alpha by 1 plus alpha whole square. So it's a different zone. It's a different zone. Similarly, the part which is above this solid black line, that is alpha beta greater than 1, that also I'm dividing into two parts. The one part which is below this red line and another part which is above this red line. So on the basis of the two equations, I can divide the relevant zone into four parts: 1, 2, 3, and 4. And shading the parts, relevant portion. This is one part, one zone. This dotted part is the second zone. This is the third zone. And this is zone 4. This is zone 4. Now please write down several points which I am marking. Please write down in zone 1, beta less than 1 upon alpha. In zone 1, beta less than 1 upon alpha, which implies the dynamic equilibrium is a stable equilibrium. In zone 1, alpha into beta is less than 1, or beta less than 1 upon alpha, which implies equilibrium is dynamically stable. Moreover, beta than 4 alpha by 1 plus alpha whole square. Moreover, beta greater than 4 alpha by 1 plus alpha whole square. Which implies roots are real. Which implies roots are real. Together the two conditions provide what type of time path? Anyone?
Ma'am, it's monotonically convergent.
Ready?
Monotonic and convergent.
Convergent time path of income. Okay. So together the two conditions provide a monotonic convergent time path of income. So in zone 1, we will have monotonic convergent time path of income. Okay. So if I draw the diagram, this kind of time path we will have. Is it clear? Next, in zone 2, beta less than 1 upon alpha, implying the equilibrium is dynamically stable, However, beta less than 4 alpha by 1 plus alpha whole square. However, beta less than 4 alpha by 1 plus alpha whole square. It is below the red line, the parabolic curve. Indicating the roots are complex conjugates. Hence, the time path of yt will be oscillatory in nature. Hence, the time path of yt will be oscillatory in nature. Together, the two conditions generate damped oscillatory. Together, the two conditions generate damped oscillatory time path of yt. Together, the two conditions generate damped oscillatory time path of yt. Okay, damped oscillatory time path of yt. Next, in zone 3, beta greater than 1 upon alpha. Everybody, zone 3, alpha beta greater than 1, isn't it?
Yes.
So in zone 3, beta greater than 1 upon alpha. Hence, the time path will be divergent in nature. Moreover, beta less than 4 alpha by 1 plus alpha whole square, indicating roots are complex conjugates and hence giving an oscillatory time path of income. Together, the two conditions give explosive oscillatory time path of income. So please draw the diagram. Okay.
Ma'am, can you please explain this one once more? Like alpha beta greater than 1.
Alpha beta greater than 1. This black line, this line is showing alpha beta is equal to 1. So any part above alpha beta is equal to 1 is showing alpha beta greater than 1. If you look at this rectangular hyperbola, the zone which are above these particular border line, their alpha beta greater than 1, that is beta greater than 1 upon alpha. So in zone 3, if you look at zone 3, it is above the line alpha beta equal to 1, and hence in this zone we will have the condition beta greater than 1 upon alpha, isn't it?
Yes, ma'am. Yes, ma'am. Thank you.
So everybody could draw up to the explosive oscillatory time path of income. Next.
Can you explain the second condition also once more? Like the beta less than 4 alpha by 1 plus alpha whole square.
Because the zone 3 is lying below 4 alpha, beta is equal to 4 alpha by 1 plus alpha whole square line. That this line is beta is equal to 4 alpha by 1 plus alpha whole square. So the zones which are above this line, for them beta greater than 4 alpha by 1 plus alpha whole square. The zones which are below this red line, for those zones beta less than 4 alpha by 1 plus alpha whole square.
Yes, ma'am. Yes, ma'am. Okay.
Next, in zone 4, beta greater than 1 upon alpha. In zone 4, in this triangular shaded zone, alpha beta greater than 1. It is above the black line, So beta greater than 1 upon alpha. And thus, the equilibrium is dynamically unstable. And thus, the equilibrium is dynamically unstable. However, beta greater than 4 alpha by 1 plus alpha whole square, beta greater than 4 alpha by 1 plus alpha whole square, indicating the roots are real. Thus, here we will get a monotonic time path of yt, Thus, here we will get a monotonic time path of yt. Together the two conditions generate monotonic divergent time path of income. Monotonic divergent time path of income. Etc. Everybody could complete it. Finally, when alpha beta is equal to 1, finally, when alpha beta is equal to 1, that means, you are on this line, black solid line, alpha beta is equal to 1. Can you tell me what will be the nature of the time path then?
Uniform.
Please try.
Ma'am, uniform.
I didn't get you.
Ma'am, uniform.
Uniform?
Uniform.
Oscillatory.
Oscillations, uniform
Uniform
oscillations.
oscillations.
Yes, very good. Because oscillatory, because this black line is below this red one. Okay. So beta is less than 4 alpha by 1 plus alpha whole square. So the roots will be complex conjugates. So the time path will be oscillatory. However, when alpha beta is equal to 1, neither it will converge nor it will diverge. Rather, it will be uniform oscillatory time path. So please add. Finally, when alpha beta is equal to 1, equilibrium is dynamically unstable. Equilibrium is dynamically unstable. Here, beta is less than 4 alpha by 1 plus alpha whole square. Here, beta is less than 4 alpha by 1 plus alpha whole square. And hence, the time path will be oscillatory in nature. Time path will be oscillatory in nature. However, the oscillations will have equal amplitude. Oscillations will have equal amplitude around the equilibrium income. Thus, we have a time path showing uniform oscillations. Thus, we have a time path showing uniform oscillations.
Excuse me, ma'am. Can you please repeat?
Ma'am, I had a question.
Ma'am, is when it is equal roots, ma'am, how it is oscillatory?
Ma'am, isn't it above the beta equals to 4 alpha by 1 plus alpha
Yes,
square?
ma'am. Ma'am, it is monotonic.
Yes, ma'am.
Look at this line. Look at this black line. Alpha beta is equal to 1. We are considering the condition.
Oh, okay.
Into beta is equal to 1. We path along this line, this line, this line. Okay?
Yes, ma'am. Yes,
This line is below or above? Beta equal to 4 alpha by 1 plus
below.
below. So beta is less than 4 alpha by 1 plus alpha whole square. So we will have oscillatory time path. Okay, everybody is fine?
Yes, ma'am. I thought you were talking about equal roots.
Okay. Now look at the diagram. If we are along these red line, you know, the PR, along PR. If we are along PR, what will be the nature of the time path? Along the path PR. Then alpha beta greater than 1 or less than 1?
Greater than 1.
Alpha into beta greater than 1. So time path will be stable or unstable?
Unstable.
Unstable. Okay. And when beta is equal to 4 alpha by 1 plus alpha whole square, you are lying on PQ. That means beta is equal to 4 alpha by 1 plus alpha whole square. Okay. So what will be the nature of the root?
Real and equal.
Real and equal. Okay, real, and it is not distinct, rather real equal. So when the roots are real, what will be the nature of the time path?
Monotonic.
Monotonic. So if I consider PR, suppose we will like to draw the time path for the incomes lying along the points PR. So what will be the nature of the time path? Monotonic
divergent.
Monotonic divergent. Monotonic divergent. And what about OP?
It is monotonic convergent.
Monotonic convergent. Exactly. It will be monotonic convergent. Okay. So in this way, we can derive different possibilities. We can talk about different possibilities, you know. Since for OPR, we are not getting similar result. For OP part, we are getting some result. For PR part, we are getting some other result. Therefore, generally, we do not mark it while we develop the theory. However, you have to look at the conditions, whether the roots are real, whether the roots are complex. If the roots are real, be it, you know, repeated real roots, be it distinct real roots, you will have monotonic time path. If the roots are complex, you will have oscillatory time path. And then you need to check what is happening regarding the other condition, the stability. Alpha, beta less than 1. Are you getting alpha, beta less than 1? Are you getting alpha, beta equal to 1? Are you getting alpha, beta greater than 1? For alpha, beta equal to 1 and greater than 1, you cannot have stability. However, for alpha, beta less than 1, you will have stability. So make a mix and match and go through the entire thing. You will understand the matter well. Okay? So if you have any question, anyone, any question. So next, we will develop the similar type of model, a very, very similar type of model. However, we will consider the acceleration principle in a bit different way. And instead of developing the entire concept in terms of MPC, we will like to use MPS, marginal propensity to save. Okay, very similar kind of model. This is the Samuelson's basic or classic framework. Later, Hicks added some inputs here, and that model is known as Hicks-Samuelson model, you know, a bit development over the Samuelson's framework. Theoretically, the ideas are very, very similar. However, if I change the acceleration principle a bit, if I instead of MPC, if I use MPS, there will be some changes in construction of the model. So we will move. Okay, Hicks-Samuelson framework, Hicks-Samuelson framework, okay. So some development or some changes made by Hicks in the original Samuelson framework. Okay, so you are familiar with the national income identity. Already we marked all these things in the Samuelson's framework. So directly I'm starting with the national income identity equation. YT is equal to CT plus IT plus GT. Whereas in the Samuelson's framework, Samuelson considered G as exogenously given, government expenditure as exogenously given, and therefore he used G naught. In the Hicks-Samuelson framework, we are considering government expenditure is changing from time to time. So we are using the notation GT. This is equation number 1. Capital CT is equal to small c into YT minus 1. So in that sense, the consumption equation is similar. I told you the beta which I used in context of Samuelson's framework, that indicates the MPC, marginal propensity to consume. Hicks clearly mentioned CT is equal to small c into YT minus 1, where small c is greater than 0, less than 1, and indicates marginal propensity to consume. And in this framework, Hicks consider MPC to remain constant. MPC to remain constant. Okay. So whatever be the income groups, whatever be the structure of the country, it is not varying from country to country or economy to economy, you know. So we are considering this to remain constant. As I discussed in the last framework, present period consumption expenditure is a function of last period's income. It is a function of last period's income. Okay. So there is a lag between a consumption and income. Whatever I am earning in the last period, on the basis of that, I am planning the consumption expenditure for the present period. So there is a lag of one period in the interrelationship between CT and YT. Now look at the IT equation, investment equation. Here, investment equation is a bit different from that of the Samuelson's framework. In Samuelson's framework, we consider IT is the difference between the consumption of T and T minus 1th period. And then when we present the start presenting the time path, etc., we replace all CT and CT minus 1 in terms of YTs. In case of Hicks model, directly investment is considered as a function of the difference in income in T minus 1th and T minus 2th period. So what is the idea? This is 2021, 2021. Investment in 2021 should be exactly equal to or will be some function of the surplus income we have in 2020. Investment in 2021 will be a proportion of the surplus income which we got in 2020. Now the surplus income in 2020 is nothing but the difference in income in 2020 and 2019. The surplus income in 2020 is nothing but the difference in income of 2020 and 2019. Okay. So in Hicks framework, whatever surplus income I have in 2020, that I'll use in investment purpose in 2021. How I'll calculate surplus income in 2020? That will be the additional output or additional income the economy got in 2020 over and above the 2019. So additional productive capacity, additional income, that will be fully invested in the next period, that is in 2021. Okay. Now investment will be quite a large compared to the actual surplus. So I defined what is the meaning of surplus, the difference between the income between 2019 and 2020 that will be invested in 2021. However, what we are getting, there is an accelerator here. V is the accelerator. Okay. So magnified, the difference will be magnified when we are moving towards investment. So it is not, V is not equal to 1. Generally, it is greater than 1. So it will be magnified. Okay. So this is the idea. So we will consider a surplus and that will be invested in a magnified way, scale up. We will scale up it and will invest it in the Tth period. So here investment is related to incremental income observed in the last period. Incremental income observed in 2020. Any question regarding these three equations? Substituting 2 and 3 in equation 1, we get yt is equal to small c yt minus 1 plus v. In case of it, I am writing v into yt minus 1 minus yt minus 2 plus gt. Or yt minus c plus v yt minus 1 plus v yt minus 2 is equal to gt. This is the second order difference equation in yt. This is the second order difference equation in yt. Here, the model has two parameters. Directly, we are getting, C, MPC, and V, the accelerator. However, in the rest of the exercise, instead of considering small c, I'll consider 1 minus c, or c will be considered as 1 minus s. So Higgs presented the model in terms of marginal propensity to save rather than marginal propensity to consume. So henceforth, C will be replaced by 1 minus S. I hope you know that C plus S, MPC plus MPS is equal to 1. Do you know that? Do you know that?
Yes, ma'am.
Yes, ma'am.
This equation can be presented in terms of savings too. Do you know that?
Yes, ma'am.
Instead of consumption in the national income identity, we can bring S. Okay? And income will be either consumed or saved if we consider the expenditure side of the national income accounting. This is the income side or the supply side of the national income identity. This is the expenditure side of the national income identity. Okay? So it can be presented in terms of consumption expenditure, or it can be presented in terms of savings, because people will either consume or save, or it is assumed that MPC plus MPS is equal to 1. Okay. So this is the second order difference equation in YT. Once we understand the structure of the second order difference equation, now you know what you have to do. You need to first find out the PI, YE, the equilibrium income. After that, we will consider the Hart operation, and we will consider, or we will derive the characteristic equation for these second order difference equation. We will derive the characteristic equation. As we derive the characteristic equation, we will talk about the roots, characteristic roots of the model. Next, we will define the complementary function. Once we get the idea of PI and CF, we will be able to get the final form of YT. Once we get the final form of YT, we will talk about the stability condition or stationarity condition or convergence condition, as well as we will talk about the fact whether the time path is monotonic, whether the time path is oscillatory, etc. So today I'll stop with calculation of YE, equilibrium income, and then I'll continue tomorrow. So if this is equation number 5, I'll tell you to derive the equilibrium income. First, you write down for an equilibrium solution, we set YT minus 2 is equal to YT minus 1 is equal to YT is equal to YE. Substituting this in equation 5, we get write the equation in terms of YE and then calculate YE.
Ma'am, YE is equal to GT over 1 minus C.
Yes. Is it similar to that of the Samuelson's framework?
Yes, ma'am.
In the Samuelson framework, what was the equilibrium income? G naught divided by 1 minus beta.
Beta, yes.
Also are getting the similar kind of framework. And here also we are finding that accelerator ceases to operate at equilibrium. So everybody got the value?
Yes,
Yes,
ma'am.
ma'am.
Solid equation number 6. Equilibrium income is independent of accelerator. As income remains stationary, accelerator ceases to operate. YE is also the value of particular integral. YE is also the value of particular integral. Okay. So I'll not move further. Actually, as I mentioned, I have to consider the difference between YT and YE. I'll go for hat operation. Then I'll find the characteristic equation. I'll derive the quadratic relevant here. And after that, I'll talk about the roots. And then we will consider B1 plus B2, B1 into B2, 1 minus B1 into 1 minus B2. Okay, and after that, the CF part. After that, I'll talk about the stationarity condition. If the roots are real, what will be the stationarity condition? What will be the stationarity condition? If the roots are complex conjugates, so similar kind of thing. However, the approach is a bit different. Okay, so this is the idea. And after that, I have to talk about, you know, the discriminant part, If the roots are real, what will happen? If the roots are complex conjugates, what will happen? Okay, so all these things I need to share with you. Okay, and finally, once we understand the basic structure of the model, we have to derive the time path of income. Okay, time path using the stability condition and using the discriminant, we will derive the time path of income. Any question?
Are there any sums that we need to do from this portion?
Okay, at this moment, for the Samuelson or the Hicks-Samuelson's framework, I have to check from Chiang whether there is any problem, which you will be able to solve, etc. The questions are mainly model based. Okay, so look at the exercise. I'll also check, and tomorrow I'll tell you about this, whether we have some numerical, we can do some numerical exercises from Chiang. Okay.
And so what kind of model?
What kind of?
Will we get from these models?
So you look at Chiang, I'll also look at this thing, okay?